This past semester, our team worked to design and simulate a low-temperature waste heat recovery system for marine fuel cell applications. This was a global capstone research project in collaboration with Chalmers University in Sweden. We are a team of 9 students comprising 5 from Pennsylvania State University and 4 from Chalmers University.
Our sponsor, Volvo Penta, came to us with a problem pertaining to fuel cells. Fuel cells are one of the cleanest forms of producing energy. A photo exchange membrane fuel cell has a considerably high efficiency of 50%. Some parts of the other 50% is dissipated in the form of heat that can be further harnessed to generate electricity. Our project focuses on developing and simulating solution concepts for a low temperature waste heat recovery system that can be used with a fuel cell.
The team collaborated in researching a number of viable concepts. We derived 3 ultimate design solutions, including the organic Rankine cycle, thermoelectric generator, and thermoacoustics, which were further compared through a P-matrix. The 6 metrics that were used to narrow down our options were efficiency, operating temperatures, production costs, operating costs, physical dimensions, and maturity of the concept.
The P-matrix revealed that the organic Rankine cycle and the thermoelectric generators were the most promising concepts that can be used for the aforementioned application. In the organic Rankine cycle, the working fluid goes through cycles of evaporation, expansion, and condensation. As the fluid expands inside the turbine, thermal power is converted into rotational power. By adding rotational electromagnetic converter into the cycle, the ORC can produce an electric power output. The ORC is an attractive system for heat recovery when the thermal power of the energy source is limited. The ORC utilizes an organic, high molecular mass working fluid which has a lower evaporation temperature than water. There are different configurations of the ORC, but at its simplest form, the ORC consists of a pump, evaporator, turbine, and condenser. For low temperature waste heat recovery, it is common to add a recuperator to the cycle, which is an internal heat exchanger preheating the working fluid before it enters the evaporator. A typical organic Rankine cycle with a recuperator is presented in the following figure.
A thermoelectric module is a device that converts thermal energy directly into electrical current via temperature difference. The flow of energy can go from thermal to electrical or vice versa, depending on the thermoelectric module. The focus of this project involves one of these 2 types of thermoelectric modules. There are thermoelectric generators, or TEGs, that operate based on the Seebeck effect, and there are thermoelectric coolers, or TECs, based on the Pulsier effect. A TEG will provide electrical generation when heat is applied to the system that causes a temperature gradient across the TEG. In this scenario, the electrical power output is proportional to the temperature difference between the TEG junctions. A thermoelectrical circuit composes of materials of different Seebeck coefficients. This would be P or N-doped semiconductors. A TEG will produce clean energy and serve as a potential candidate for transforming low temperature waste heat into electrical power.
As you can see, each of these simulated systems is better in their own way. While the TEG is novel, it has limited moving parts and is inexpensive to operate. Meanwhile, the ORC is a tried and tested method of heat recovery. Our ORC design provides a power output of 25 kilowatts, which equates to a recovery efficiency of around 5%. On the other hand, the TEG system has high installation costs and provides only a 1 kilowatt power output. This can be due to the low pressure needed during operation for our current system design. Moving forward, the TEG has promising potential to be optimized for much better efficiencies. Our team would like to give a huge thank you to our sponsor, Volvo Penta, as well as our examiners at Chalmers University and Penn State. Thanks so much for watching.